Hi everyone, Mr. Lee here. In this video, we're going to go over more two-dimensional Newton's laws problems. We're going to be focusing on hanging objects. All right, let's get started. So the first thing that I want to do is I want to draw a picture. Let's say we have, I don't know, a squirrel. Look at that. That's a beautiful squirrel right there. Okay, so we have a squirrel, and this squirrel is sitting on a wire, like a telephone wire. And the squirrel bends the telephone wire like so. Now, there's a lot of things that we can figure out from this scenario alone. Before we start, let's do a quick free body diagram. This free body diagram, let's make that the squirrel, we're going to call this the force of gravity. Because the squirrel is sitting on a surface, we can say that there is a normal force, like so, holding the squirrel up. All right, and we have here the wire. So the right part of the wire, I'm going to draw arrows here, is pulling up and to the right. So we're going to call this T1. Once again, this right wire is pulling up and to the right, and this left wire, we're going to call this T2, is pulling up and to the left. Alright, so this is a free body diagram. I like this free body diagram, and I'm going to just make a couple of statements. We're going to say that we are in equilibrium. Now, equilibrium just means that there are no external net forces. So what that means is that all the forces, when they add up, equal to 0. Now this is extremely handy because we know that this is Newton's F equals ma, and if the net forces add up to 0, that means that your acceleration here is 0. Now this is very special. This is a very unique situation, and it makes our math so much easier. All right, now, so this is a free body diagram, and I will submit that for my answer if the problem was asking for a free body diagram. Next, what I want to do is I want to break this up into components because we can't do math with a angled force like this. Okay, we got to break it down into this x and y components. But before we do that, I'm going to create the horizontal. Okay, so this is my horizontal. Now what that means is that the angle is in respect to that horizontal. We'll call this theta 1 and we'll call this theta 2. All right? Okay. So if I wanted to break up T1 into its components, I would break it out like so. I take a look at T1 and I think to myself, oh, okay, T1 is being pulled upwards and to the right. And so my component will reflect that. This is my horizontal component. Okay, so this one will be called, I'm going to make this tiny, a little smaller. We're going to call this T1X. Okay, because this is along the x-axis. Notice here my arrowhead is pointing to the right, and that's because this tension is pulling up and to the right. Your components have to reflect what's going on in the real world. All right, the next one I'm going to do is T1Y. Just like that. All right, so we have T1X and T1Y, and we have the angle. All right, I'm going to do a little sidebar over here. And I'm going to create a equation for both T1x and T1y. Now, hopefully you watched the previous videos, so you should know that we're going to be using the Pythagorean theorem here in order to figure out what to call T1x and T1y. So let's do the red one first. Okay, so according to this angle theta, T1x, okay, T1x is adjacent to this angle. So if we bring up our trig functions, so katoa, okay, when it's adjacent, we use the cosine. So we can say that the cosine of the angle is equal to the adjacent over the hypotenuse. Okay, so that's what the trig cosine looks like. And if we were to plug in the known values, we will say the adjacent is T1x and the hypotenuse is T1. Therefore, T1x is equal to T1 times the cosine of theta. All right, just like that. Now I'll take a shortcut here for T1y because once you do enough of these, you start to see a pattern. The pattern is you want to identify the trig function. So here T1y is opposite of this angle. So opposite is sine. So we have the sine of theta, and in front of it, we always put in the hypotenuse. In this case, it's T1. Okay, so let's use that shortcut over here on this other side. Okay. Once again, I'm going to add the horizontal component like so. I'm pointing this one to the left. Now this one is going to the left because this tension is pulling up and to the left. We're going to call this T2x, and up here it's being pulled up, so we're going to call this T2y. And of course, this being a right angle. Now if we were to use our shortcut, we would say that T2x is equal to, because this is the angle and this side is adjacent, we use cosine of theta. In front of it, we always put the hypotenuse. This side over here is opposite of that angle. So the opposite, we always use a trig function of sine. And in front of it, we put the hypotenuse. Now, I do want to point out that the steps that I'm taking here, they work for these scenarios, but depending on what your triangle looks like, your opposite might not always be, or excuse me, your y might not always be the sine. Okay, sometimes your vertical leg of the triangle, it could be cosine. Okay, so just be careful with that. All right. Okay. So here we have our components, and it's broken up into its pieces. So if I wanted to create a net force equation based off of what we just discovered here, I would do it like so. I'm going to do the first one down here. We'll call this the net force in the x direction is equal to mass times the acceleration due to gravity along the, mass times the acceleration along the x-axis. So same strategy. We want to identify all the forces along the x-axis. So I'm going to start off with my normal force. Okay, at the 12 o'clock mark, and go around the clock. I'm going to ask myself every single time, does this belong in the x-axis? So normal force, that does not belong. T1, that does not belong. T1y, that does not belong. T1x, that belongs. Okay, and it's pointing to the right, so we will write that as positive T1x. What about this weight? That does not belong. T2x, that does belong. Minus T2x. Remember, that's a minus because it's pointing to the left. T2y, that does not belong. T2, that does not belong because that's at an angle. It's neither an x nor y, but a combination. And we're back to the start. Now, you might find this to be a little bit tedious, but trust me when I say that this is a skill set that I do, and I encourage all of you to do so, just so that you don't accidentally miss a force. Okay? Because when we get with more forces, it's going to be a little bit more hectic. All right, so here's our net force equation. Now, here's a little trick. Remember, this system is in equilibrium. That means our acceleration is 0. So that makes our math so much easier. So we have T1x minus T2x is all equal to 0. This just means that it's not accelerating in the horizontal axis. So we can even rearrange this to say that T1x is equal to T2x. Okay? Now, up here we solve for T1x. We broke it down even more, so we could add that as well. We can say that we have T1 cosine of theta. I got that by plugging in this value right there. And T2x, I'm going to take what we figured out over here and say T2 cosine of theta. So if a problem is asking for, what is tension 1? Well, if I have this equation here, I could rearrange the variables so that I can say that tension 1 is equal to tension 2 times the cosine of theta divided by the cosine of theta. All right. Oh, excuse me. This should be theta 1 and this should be theta 2. We got to be very careful. I should include that up here as well. This is theta 1, theta 2. This is theta 2 and theta 2. There we go. All right, so if I were to submit this as an answer, this would be my answer for variable form. And then if I have numbers, I will plug it in. Let's try the y-axis. So we have the net force along the y-axis is equal to mass times acceleration times x. All right, same strategy. I'm going to go to my component drawing and ask myself, does this belong? Does this normal force belong? Yes, it does. It's going up, so it's positive. What about this T1? That does not belong. T1y, that does belong, and because it's positive, I'm going to write that as, because it's going up, I'm going to write that as a positive. What about this T1x? Does not belong. This f of g, that does belong. What about this T2x? Does that belong? That does not belong. What about this T2y? Does that belong? That does belong. and we have t2 here. That does not belong, and we're back to the start. All right, once again, that might seem a little bit tedious, but trust me when I say it's better to go through the motions rather than make a mistake. Like I just said right there, I wrote that as a sub x instead of a sub y. All right, so in order to make this a little bit simpler, we're going to substitute in the zeros where they belong. We know that the acceleration is 0 because it's not accelerating up or down, as in the squirrel. And so the next step, I'm just going to clean it up a little bit. We got t1y minus f of g plus t2y is equal to 0. All right. So here we have our equation. Now we can break this down even more because we know what t1y is, right? We can say normal force plus, we said that the t1y over here is t1 sine of, oops, that should be theta 1. My mistake. Boop, there we go. Theta 1 minus the weight is just mass times acceleration due to gravity plus t2, which is over here. We can say it's t2 sine theta 2 is all equals 0. All right. Now, based on the problem, we would rearrange this equation so that we are solving for a single variable, whatever that might be, and we should be able to solve it. Now, oftentimes, you're going to be asked to combine the two tensions. So the tension that you find here can always be plugged in there. And if you do that, you could also find T2. It's a cool little trick that they do. All right, so that's one problem. I'm going to do another one. This one is called the hanging sign problem. The hanging sign. So let's say we have a building. Okay, so this is my building. All right, just like the side of the building, and on the side of the building I have a sign like so. Okay, and this sign tells us that this is a, I don't know, this is a bakery, all right, where you can buy bread and stuff. All right, so we have a bakery. All right, now with this picture we can come up with a free body diagram. The free body diagram, the first force will be going down, F of g, that's the weight. We have a force along this rope. We're going to call that T1. This is called tension 1, and this rope is pulling the object to the left. We're going to call that T2. Now, here's a reminder: ropes can only pull. Okay, ropes can only pull. All right, and that will be a free body diagram. Notice the lack of the normal force, and the normal force is not there because it's not on the surface. All right, let's break this down. So I'm going to create the components here for T1. Oops, let's make this theta, whatever that theta might be. So T1, so here we can write T1x, and along this vertical axis we can call that T1y. All right, I don't have to break up T2 because there's no angles. All right, now also recognize that this is an equilibrium because swinging signs above stores is extremely scary. All right, next we're going to create a net force equation. Let's do one for x first, okay, which is max. All right, now we don't have a 12 o'clock, so the closest one is T1. I'm going to start there. I'm going to ask myself, does this belong in the net force x equation? And the answer for T1 is no. What about T1y? Does that belong? That does not belong. What about T1x? Does that belong? That does belong. What about f of g? Does that belong? Does not belong. What about T2? Does that belong? That does belong. I'll put that in as negative T2 because it's going to the left. And once again, we're in equilibrium, so our acceleration would be 0, making the whole right side 0. All right, now we can rearrange this and say that T1x is equal to T2. And upon further breaking down of the equation, we see here and we see that T1x is adjacent to this angle. So we can say, taking our shortcut, T1x is T1 cosine of theta is equal to T2. Now I use cosine because it is adjacent, right? So we found T2. Okay, and if we divide both sides by cosine theta, we can find T1 as well. All right, next we can find f of y. Just like that. Now, always, we are in equilibrium because swinging signs are dangerous, and we don't want that dangerous scenario in front of our bakery. All right, so we can say 0 over here, and we're going to take a look at all of the y forces. Okay, starting with T1. Does T1 belong? T1 does not belong. Does T1y belong? T1y does belong. Here's a little clue. There's a y there. What about T1x? T1x does not belong. What about the weight f of g? Does that belong? That does belong. And it's going to be negative because it's pointing down. What about T2? Does that one belong? That one does not belong because that's along the x-axis. All right, so here we have our equation, T1y minus f of g is equal to 0. We can swing the f of g on the other side. All right, and at this point we can break this down even more because we know that the forces of gravity is just the mass times the acceleration due to gravity. And T1y is, well, if we take a look at the angle here, we see that T1y is opposite of the angle, and whenever it's opposite of the angle, we always use the sign. Okay, and it's the hypotenuse times the trig function. All right, so what this means, okay, now this is cool. This is where the physics comes in. What this means is that the entire weight of the sign is being held up only by T1. It's only being held up by T1, and not all of T1, but just the vertical portion of T1. Only the part that's holding it upwards is holding up the sign. So there's a lot of stress and tension along that rope because that rope has to hold up the sign all by itself. So if I were to ask you, what is T2 doing? Well, simply put, T2, the only thing that T2 is doing is to prevent this sign from swinging out like this. Because if you could imagine, if we were to get like scissors and cut that rope, okay, this sign will swing outward like that because we removed that tension force, all right? And if we were to cut this rope right here, we could imagine that this bakery sign will swing downwards like so, because nothing is holding up the weight on that end either, okay? All right, wonderful. See you next time. Bye-bye.